Hello, everyone. Am I audible to all of you?
Yeah,
Pawan sir, am I audible? Everyone, yes. Maybe I'm audible to all. Pawan sir, are you getting my voice, sir?
yes,
Good evening to all of you. Sir, a very warm welcome from our side, sir, from Mandsaur University. I, on be- I, on behalf of Mandsaur University, welcome you. And today we are going to speak about
Hello, am I audible to all?
Yeah,
Okay. Very good evening, sir.
yeah. Good evening.
Okay. Am I audible to all? Very good evening to all participants. Am I audible to all?
Yes.
Hello,
Huh?
sir. Are you hearing me?
Yeah, I can hear you. Can you hear
Okay.
me?
Oh, yes, sir. Yes, sir. Yes, sir.
Okay. Yeah,
Yes, sir.
sure. Yeah.
Yes, sir. Sorry for disturbance, sir.
That's okay. Yeah, please go ahead. I understand.
Okay, 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 sir. Okay, sir. First of all, I would like to address our speaker. I would like to introduce our speaker, Dr. Raj Subhash. He has completed his PhD in 1985 from Concordia University, Montreal, Canada. He has very huge experience of industry. His expertise in design and servicing of steam gas turbines, generator, compressor, fans, pump, automobile axial, and so many things. Fans, pump, and right now he is vice president. So I hand over the session, Dr. Raj. Sir, please.
Okay. Yeah. Thank you, sir. Thank you, Professor Bhavan, for introducing me. Thank you so much. And I would like to thank Dr. Gaurav Gugliani and Dr. Ravi Kumar. At this point,
Yes.
I will.
I would like to thank Dr. Gaurav Gugliani and Dr. Ravi Kumar. At this point, I would like to thank Dr. Sorry, Dr. Raj sir.
Yeah.
Sir, your picture is showing dark.
Oh,
Please come
okay.
in light. Raj sir. Sir, your picture is showing dark.
Yeah, I
Please come in light. Sir, your face is not visible proper, sir. Please come. Yes, 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 yes. It's fine.
yeah,
It's fine,
okay.
sir.
Okay. Okay. It's saying
Sir, your face is not visible proper, sir. Please come. Yes, yes, yes. It's fine. It's fine, sir. So shall we start, sir, session?
yeah, sure. I'm ready. I can start right now. I'll share my screen. Can you see my screen? Can you all can see my screen?
No, sir. Your screen is not visible, sir.
Oh, screen is not visible.
Uh, Sir, in status bar there are one, 2, 3, 4, 5, 5 menus. First, mute. Second, start cam mic, and then share screen.
Yeah.
Click on share screen. Then please.
Yeah, I share screen. Share your entire screen. Just 1 second. Uh, so I'm trying to share my screen, but can you see my screen?
No, sir.
No. Oh, whoops. Okay, I'll try again. I'll try
Yes,
again.
yes, sir. Please.
Um, share screen. So it says share screen. Share the entire screen. I'm clicking that. Can you see that? See my screen? Can you see my screen now?
No, sir. No, sir. Your screen is not visible, sir.
Oh, okay. Okay. Can you see my screen now? Can you see my screen? Can you see my screen?
Sir, your screen is not visible. Sir, please click on fourth number option, share screen.
Yeah,
Then
yeah. Mm. Okay. Can you see my screen now? Yeah, can you see my Can you see my screen now?
sir, you have to do that. Click on share screen button, then OK. Sir,
That's what I'm.
click on share screen. Yes, 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 sir. Yes, sir. Your screen is visible, sir. Your screen is
Okay.
visible, sir.
Okay. There's background
Sir,
noise. Can you? Yeah. Somebody has to mute. It's okay. Yeah. Some. Hello, all. Hello, all. Can you hear me?
yes, sir. Yes, sir. Sir, sir, put off your echo sound, sir, please.
What is that?
Sir, echo sound is coming from your side, sir.
Oh, my side.
Yes, sir.
Oh my God. How can I control that? I'm trying my best. Can you hear me?
Yes, sir. Yes, sir.
Yeah. Okay. Now, what is that sound? I don't understand why that's happening there. Yeah, this is my computer. Can you hear me? Can you hear me?
Yes, sir. Yes, sir.
Okay, but yeah, can you hear me? Now can you hear me?
Yes, sir. We can hear you, but echo sound is come from your side, sir. Please off one mic from your system, sir.
One mic.
Yes, sir. It
Uh,
gives too much echo sound, sir.
okay, so how to do that? Audio mic. Is that okay now? Still, is it okay now? I
So, are you using your internet connection from your handset?
no, I'm using through my laptop.
Okay, sir.
Now it should be okay.
Yes, sir. Yes, sir. It is okay, sir. Now.
Yeah, okay. So can we start now? Sorry for the all the disturbances. Yeah, I'm sorry. And
Yes, sir.
yeah,
Yes, sir.
we'll
Yes.
start. Yeah, we will start. Okay. Yeah. Good evening, everyone. Hope this will go smoothly. So here I want to present something. The material and information presented here is for general information purposes only. No one must copy or videotape or capture on mobile phones or any other electronic device. The material presented here must not be used to do business for any other information. No transmittal by video or audio, please. Okay. So with that start, I will I will go to the subject. Okay. So can you hear me well now?
Yes, sir.
Okay.
Yes, sir.
So um, now why we are talking about vibration today? So that is the big question now. So what I found was from my experience, I have been uh, handling or tackling problems all over the world on turbo machinery, and I was also in contact with industry leaders and academic professors. They all have the same view, so I'm just presenting what their view is. Vibration issues are on the rise around the world, but there are very little knowledge available, or people are not coming forward to do the vibration analysis or vibration courses. So that was one thing I found. So the knowledge of vibration is essential in order to uh, solve the rotating machinery problems. So if you don't have that knowledge, it's very difficult. So from my own experience, I can say that when I was in IIT Delhi, I was electing a course called vibration analysis, and we had about 20 people first day. And after seeing the professor's presentation with all the equations, the next day it dwindled to five. And in the end, only two people were there. So I was one among them. So that was also, I'm talking about long time ago. So that means, the vibration subject is mathematically oriented or intense. I know that, but it is it is the vibration code should be taught in a way that less mathematically intense. We can explain the logic and etc. etc. And these days, in order to analyze, we don't have to go through the mathematical equations, or you don't have to develop any mathematical equations. There are a lot of well proven tools like finite element analysis that can be applied. Okay, so this the basic thing why I'm doing this is because it's mathematically intense and it discourages people learning it. So gently remind that now this has to be handled uh, really well, very well. I mean, uh, so that way, people come forward and learn this subject. Okay, now I'm into this subject. Basically, whenever you have bodies that possess mass and elasticity, they are capable of back and forth or oscillatory motions called vibration. That is for sure. Everybody knows that. That's a basis. And the vibration has both bad and good effects. In that case, I will just touch upon the bad vibration part. Excessive vibration amplitudes are detrimental to machines because now the vibration is high, and if they keep operating the machine, and eventually they run out the parts and they will break down quicker than they thought that it will work. So that's why we don't want to keep the vibration at beyond certain levels. So there is a limit. And also it is not only that, it's harmful for environment as well as humans and animals. No, you it's an annoying noise. No one wants to hear that. Here I want to say that even the bad vibration has also good effect. For example, people raise pets, for example dogs, and they want to make sure they don't cross the certain boundary. So they create some kind of peripheral vibration and they stay within that periphery. It's a vibration with a high frequency noise. So the dogs, when they reach the boundary, they cannot go beyond that. So that way, it helps. So the even bad vibration has some good effect. Now, really going to the good vibration part, vibration effects are used to separate out dissimilar materials. That they are doing it with a sieve or a belt that is vibrating at a particular frequency. It's easy to separate different materials. And the second one is acoustic vibrations generate pleasant musical sound that is consisting of several frequencies, natural frequencies combined, is a harmonics. So, but you have the player has to tune different harmonics to the best of their ability and get the meaningful neurological impulses into humans' brain, basically. So that's another good effect. And if you look at the the heat transfer happening between one source to the other. For example, you want to heat water. You keep the pan on the stove and pour water. What happens is the heat coming from the stove goes through the solid material, which is basically consisting of atoms. And that atoms, when the temperature increases, they vibrate. Because of vibration, the heat is transferred from one to the other. The same way, the heat is transferred to the fluid or the water inside. The same way, it's a vibration of atomic particles. So everywhere is vibration. Vibration is very, very important. You name it, you have it. Even human minds, if they have vibration, then they achieve something. So that's a vibratory dream. Okay, so in it's important to understand the vibration in depth and its characteristics in order to solve problems. World's problems are not just one or two; there are multiple problems. So if you understand the vibration characteristics, it's easy to resolve those problems. That's the beginning of this slide. Now, I would like to go and explain what is static and dynamic design, how they are different from each other. Then from there, we go to vibration basics, mathematical expressions, and single multi degree of freedom systems. So basically, statics is a subject that deals with the behavior of a part or a machine under steady operating conditions, okay, or steady applied loads. So usually, if you design a part, you're basically looking at the stress, mechanical stress for a particular force or applied force, and that's the only thing. With that, if you meet the stress levels, then you say that that design is done, and then that goes into production, and the part is manufactured, or a structure is manufactured, or a machine is manufactured, and then it is supplied. And that machine will be working for how many years, we don't know, 10, 20, 30, whatever. And eventually that machine has to the parts can wear out, and the vibration problems may creep in. Okay, so that's where the dynamic comes. Okay, dynamics is basically a subject that deals with the part under dynamical forces or conditions. The main parameter that we measure for the dynamical force is vibration. That's measured under whatever the dynamical force. It could be several. It could be an impulse force, or it could be a steady state load, whatever. But still, it's a vibratory load. Okay. So vibration is evaluated to find out the severity of a part. If this vibration level is
Sir,
low,
sorry to disturb you. Your PPT is not visible for us.
oh, is that right? So
Okay.
I'll go ahead and share the screen again.
Yes, yes, sir. Yes, sir. Please
Okay.
share your screen.
Okay.
Sorry to interrupt you.
Oh, yeah, yeah, that's fine because I don't know what's going on here.
No
Uh,
problem.
yeah, just 1 minute. I lost the video. I have to go and look at the video. Yeah. Can you see my screen now?
Yes, sir. Yes, sir. You
Yeah,
just you share your screen now, entire screen.
yeah. I scared. Yeah. Can you see my entire screen?
No, sir. No, sir.
No. Okay.
Please
Just
click
one
on
second.
the share screen. The bottom. There is a bottom
Yeah,
option.
yeah. I'm doing that. I don't know why this is not happening.
Also select the entire screen. Option is
Yeah,
there.
yeah, yeah. No, that's what I'm doing.
Okay, sir. No.
Can you see that? See the
No.
screen?
Yes, yes. This is your this entire screen. Please
Oh,
open your PPT, sir.
Yeah, I opened the PPD.
Yes, sir.
Uh, you can see. Can you see now?
No, sir. Just
Oh
a wait.
no. Okay.
Sir, when you open the PPT, your PPT, you just see your PPT only. You don't see us.
Yeah, I'm doing that.
Okay, sir. Okay.
Sorry for all these
We,
things
we, we,
happening.
and we are able to see you, sir.
Yeah. Okay. Can you see the screen now?
No, sir. No, sir. Just I have seen the screen only, not showing the PPT.
No, screen only, not showing the PPT. Okay, just one second. I will go over. Say
Sir, just click the share screen.
share screen.
Yes.
Mm,
Some message is there.
uh, application window. mm,
No, entire screen,
yeah, entire
not
screen.
application, entire screen.
Entire
Okay.
screen.
Yes,
Can you,
yes. This is good.
can you
This is
see
good.
now?
Now. Okay, sir. You do the full screen. Okay, sir. This is good.
Okay.
Okay.
Sorry about that. Yeah.
Yes, 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 yes. Continue,
Now
please.
can you see that? Okay. Okay.
Okay.
Now
Thank you.
I'll continue. So it's
Okay.
basically dynamics is the subject dealing with the behavior of part under dynamical forces. So vibration is the parameter we measure in order to understand vibration and how to control vibration from that. So the focus of discussion here is vibration, okay, of rotating machinery. Now, I want to just give you a very brief, basic idea of what is happening here. If you see on the left-hand side, point B is um, traveling around the circle with a radius A, and the vertical projection of B is plotted here on the right-hand side, as you see. So each point, whenever the point moves, so we are plotting it. So you see that sinusoidal curve. So our one complete circle. You see for 360 degree, you see one sinusoidal curve, positive and negative. So this is called one period, one um, also the frequency with which this is moving, the point is moving, is omega. Okay, so at any instant, the vertical amplitude x is a sine omega t, which is a is the maximum amplitude on the curve. Okay, so the expression for vibration is given in equation 1. That can be written in a complex algebra, like is shown here, x e to the I theta I omega t, which is also a cosine function and sine function, summation of that. Okay, and the frequency f can be measured in a specific time interval. You can convert that omega is nothing but 2 pi. It goes through full circle and divided by the time. So this is what the rotating frequency is. But the rotating frequency can also be called a natural frequency if the omega reaches the highest amplitude in the spectrum. Okay, so there is no real clear definition of F and omega. They both are very similar. It all depends upon when omega reaches the maximum peak value, it's called the natural frequency. So equation 1, as I write before, a sine omega t, that can be converted to linear velocity, linear acceleration by differentiating them. So thus far we have vibration caused by a single frequency, omega. Okay, that's what we have seen. So from this, the basic parameters of vibration are frequency, amplitude, and phase angle. So whenever there is a vibration problem, the engineer should tell people or to experts when he wants to explain the problem, what is the frequency of vibration, what's the amplitude and phase angle. These three informations are very important in order for the other people understand what's happening. So, in general, in a machine, it's not just one frequency, multiple frequencies participate. So that's why the amplitude consists of multiple frequencies. Okay, is cosine omega t of A1 and B1 sine omega t plus C1, C3, D1, all those things are different frequencies. The bottom line is multiple frequencies can cause the amplitude. So here you can see that. So this is the 1x part. So one node at the middle. So this is a 3x, 1, 2, and 3, 3x. Similarly, you have 6x, 8x, 10x, whatever. So in reality, you measure the vibration. That's a combination of all these frequencies. That's what we measure. It's a resultant motion, resultant vibration profile. So that's what you measure. So it is not a single frequency, it's a multiple frequency. So it is very, very important to understand which one is causing this problem. Sometimes the frequency 1x may be dominant and the other frequencies may be of minor importance. So you will be able to find out, okay, this causes the highest vibration. Accordingly, you will see this shape of the profile will also indicate. Okay, so the periodic motions are repeatable periods of motion with multiple frequencies superimposed. That's a harmonic motion. Okay, and in general, there are a lot of machines. I can give you examples. You can see automobiles. They have rotors, aircraft engines. They run on rotors, windmills, and motors, pumps, processing plants, and also the large steam, gas turbines, and generators. They all have the main lifeline is a rotor. Without rotor, no component or no turbine can produce power. Okay, so any machine that has rotating part, they all fall under the rotating machinery category. Okay, so let us see how the structures are simulated by mathematical model in order to get the vibration. That's the rest of my lecture. Okay, so in general, as I told you, I'm concentrating on the steam, gas, and generator part used in the utility turbines. But this the whatever I have been talking about is applicable to all rotating machinery. Okay, don't forget that. Okay, so in the turbine design analysis, there are a lot of different analysis done: thermodynamics, fluid dynamics, all those things. So and then finally, the rotor dynamics is the most important part, because without rotor dynamics satisfied in the design phase, the product is not going to work. Okay, so here I'm showing a double flow low pressure rotor, steam turbine rotor. As you can see, steam goes in both directions. Okay, and it goes through the stationary and rotating blades. And these blades are different in length, as you can see, because the fluid is expanding. PV is constant. The pressure is, the volume has, the pressure has to reduce, then the volume has to increase. So this is what's happening. The fluid is expanded, okay, expanding, okay, and in both directions, as you can see. And this is the hardware. I can show you the front part of the blades are very, very small, as you can see here, and then end blades are the long blades, okay, and that they are the problem causing for the rotating machinery, because they can break at the tip or at the root areas, and in that case the turbine cannot operate, because that will become a missile and they can cause a lot of problems. So this is an opposed to steam flow machine. Steam expands axially, produces mechanical work. This mechanical work is converted to get electricity if you attach a generator, okay, to the steam turbine, okay. So rotors, blades, bearings, cylinder, and pedestal support, they're all designed. Everything here. So you see this rotor is supported on two bearings, one here and one here as well. And they also coupled to the other component through coupling. And the vibration is measured, as you can see, vibrometer here, okay. And then similarly, gas turbine. Gas turbine has two parts, compressor and turbine. Compressor basic function of a compressor is the gas is compressed or the air is compressed into the compressor, and the fuel is added to it, and it becomes a compressed air fuel mixture, okay. And then that mixture is expanded through the turbine, where the actual work is happening through expansion of the gas air gas mixture. Work is carried out, and that work is supplied to the generator to convert into electricity, okay. The flow path here is optimized based on the desired performance, because the customer wants performance. That's their goal, because that's where they make money. In order to get good performance, you need to have more stages of blades. Then only it can expansion is possible, and more work is done, and the performance is great. Okay. Then this is a generator, as you can see, stator and rotor. Stator consists of a series of magnets that produce magnetic field. When the rotor rotates in between the magnetic field, they cut the flux lines and the current is produced. Okay, that is the basis of the generator. So this current or voltage, the current is basically extracted and stored. And for a Aero engine, you can see the Aero prop wheel is drawing air from outside, and it is sending to it's basically a gas turbine. So gas turbine blades, and then turbine, compressor blades, compressor blades and the turbine blades, okay. So the air is going through that and mixes with the fuel, and that reaches very high temperature, and then that output is put into the turbine. So the turbine is basically expanding. So expanding means it's doing work. When it's doing work, it will produce. It can produce electricity if it is connected to the generator. Okay. So everywhere, wherever you see, rotor plays a very important part. So we'll talk about the 1 degree of freedom model. It's basically a single mass and stiffness model. So it's a single degree of freedom. You can easily calculate frequency, natural frequency. It can be converted to RPM as well. That's what you are seeing here. So in general, K root K over M is the natural frequency. Okay. And for rotors, omega can be converted into RPM this way. Okay. This is what we do in the rotating machinery design. In this case, how you model slightly complicated models. For example, the same single mass is supported on two support springs. These support springs are parallel, so you can combine the shaft stiffness and the support stiffnesses as well, and you can calculate the equivalent stiffness, but the mass is same as before. The mass is exactly same. So the natural frequency is square root of K equivalent over M. And now that K equivalent will have a different number, because K equivalent is not same as K. K shaft is a number, but if you include the other stiffnesses, the overall stiffness will be lower than the shaft stiffness. So this frequency you calculate here is lower than the calculated here, the frequency calculated here, or the critical speeds, NCR, is higher than the NER1 here. We call it NER1. I hope that also the same. Yeah. Okay. So the NER is different from the NCR because the support conditions changed, even though the mass, etc., everything is same, but the support condition could change the frequency. Okay. And similarly, you can do a 2 degree of freedom model where you have two different stiffnesses on orthogonal directions and two ends. It's basically a Jeffcott rotor. So in this case, if the stiffnesses are all identical, then you will be able to see a circular orbit here. But when the stiffnesses are different from one direction to the other, then you may not be able to see a circular orbit. It could change because of the dissimilar stiffness. It could be an elliptical orbit. Okay, it is. So that's what I'm showing here. The two different directions, you can create equations, and then you can solve them together with the centrifugal force. That's an imbalance mass here. Okay, so if the support stiffness are same, rotor executes circular work. When the rotor is supported on oil film, the asymmetric nature of the oil film produces dissimilar support conditions, leading to rotor whirling elliptically. So that's what I told before. Since you don't have the similar displacements in X and Y directions, so the whirl or the rotor whirl is different. It's an elliptical whirl. And here I want to give you some feel for the support conditions. Okay. For example, if a rigid support condition, the rotor has basically several critical speeds, but we are interested in only two critical speeds before the operating speed. First bending and second bending. When it's supported on rigid concrete, the first bending is reported here as 2300 CPM, and then the second bending is 5300. The moment you place that same rotor on a flexible support pedestal, it's called pedestal, then you can see a drop in the critical speed. That means the overall system stiffness is mellowed down, or is very flexible comparatively. Okay, so the critical speed also dropped, and on top of it, the next one, you also introduce oil film bearing. In that case, it has got uh, shaft stiffness, oil film bearing stiffness, and pedestal support stiffness. there are three different stiffnesses that can bring the frequency still lower. Okay, 1300 and 2600 here. Okay, I want to show it. The what are the methods we do for the for evaluating the critical speeds and displacement, etc. There are two methods in general. It's called transfer matrix method. Basically, the the beam is basically divided into several parts, and you create field matrix for the beam, and the mass points are lumped between the nodes. Okay, in between the nodes. Okay, so if you go from back end to the front end, you will see that the last state vector, the state vector is basically displacement xy, and then also moment. Moment means, the rotating moment. Okay, that can cause the angular displacements. Okay, so we have, say, 4 degrees of freedom here, and the state vector is connected to the field matrix, which defines the flexibility of the beam, and then point matrix, which defines the mass at each nodal point. So you can go on multiplying all these things until you reach this end, where it is the boundary condition is 0 at that point, because there is no support there. So the moment and the displacements are 0. So you can solve this, and you can calculate frequencies, you can calculate displacements, etc. And similarly, the finite element is a different method. It uses 4 different the parameters, like x, y, u, y. It's a different number, different notations, but they mean the same thing: displacements and the moment. Okay, so we apply 4 parameters from one node point to the other, and we assemble the matrices. Okay, the stiffness matrices uh, from for one element, and the second element, and third element, and so on and so forth. If we assemble all of them, then you can also get the mass matrix at the node points, and you can solve similarly, which you have done for transfer matrix. So both methods are very similar. They produce exactly same values. So these are the solution methods. And the third one is the modal analysis. Modal analysis provides information of different modes of vibration. Different shape can be taken by the structure during vibration. For example, you can see that this is one mode of vibration. This is another mode of vibration. The call is fundamental mode, maybe second mode. This is a twist mode. Okay, so the important thing, important information I want to give you is each mode has its own frequency, unique frequency. For this mode, there is a frequency x1, and this one, the frequency is different. So each mode is associated with its own frequencies. Okay, so here I want to show you a real turbine supported on 2 bearing supports, and we can combine the stiffnesses, stiffness of the shaft, stiffness of the oil film, and stiffness of the pedestal. Okay, if you combine all of them, the equivalent stiffness, just I'm giving an example. If the shaft stiffness is only 5 units, and then film 10, and pedestal 15, if this being the case, the equivalent stiffness is lowest of the lower, okay, of the stiffness. So it is 2.7, which is lower than the shaft stiffness. That's what sorry I want to mention to you. So it is one of the things really we are interested in 2 modes. One is the first bending mode here, and the second one is the conical mode. Okay, This is a conical mode. So these are the two main modes in any utility turbines. Sometimes you may have another mode which will be a W mode, okay, like this. Those are the three modes we get at the most. So there are no other modes, but in other structures you will be able to see more modes. So the typical modes on the rotor for the above rotor is only um, bending mode. Sorry, what happened? Sorry about that. Um, Bending mode and conical mode. Okay, so as I told you before, you don't have to you develop any mathematical equations. Those are all the thing of the past. Now the finite element model is very easy and you can apply it to any structures and it can be solved within it. Even large structures, you can do it within a day. You can get the results. So the technology has advanced so much, so you don't have to rely on the mathematical equations on all those things. So here, what I'm showing here is the double flow LP rotor, and we model using finite element and bending mode was simulated. And here, what you are seeing here is the stiffness and diameter variations. Okay, you will be wondering that, okay, I'm doing all this analysis. If I split it, because now you have to what you call divide this continuum into small pieces, then only you can model them. So when you are doing this, you may think that, no, okay, I'm dividing this area, then the mass is the whole thing. Then you may assume that stiffness also will be the outer diameter of this section, but that's not true. So what you are seeing is the stiffness behavior of the structure. So it is not to the outer diameter, it's somewhere in between. So how do we know that? So if you make a model, finite element model, and solve it using strain energy method, then you will be able to plot the distributions, stiffness distributions. That's why it's called equivalent stiffness diameters. Okay, so this is very, very critical. If you, instead of using this, if you use the outer diameter, your results will be in error. You cannot calculate the right frequencies and displacements. Okay, so what you are seeing here is the two-dimensional analysis, just showing the stiffness simulation. Okay, so the idea, I want to emphasize here that no, there is a separate stiffness diameter compared to mass diameter. Okay, mass diameter is easy to calculate, but stiffness diameter, you have to use this method. So this two-dimensional model for lateral analysis, bending, vibration, and also we can perform three-dimensional analysis of this HP rotor, LP1, LP2, and generator. So you can do it. So three-dimensional rotor models. So this is one of the results I want to show you. Don't be panicked, because this is basically an exaggerated view of the behavior, dynamical behavior of the rotor. This is a second mode, rotor second mode, and we are basically plotting the displacements due to a force, okay, and at different bearings locations. If you plot those amplitudes, you will see the shape of the mode shape of the rotor looks like this. Okay, and this is of course a structure supporting the LP rotor. Okay, and for the generator body, I have to mention here the generator cross sections, they are not uniform like steam turbine rotors, because they machine slots to accommodate the segments around the rotor. So those are all the wires, coppers, etc., etc. they will include in order to um, get the armature ready. So armature rotor is ready. So in that case, so if you properly compensate whatever the materials taken, you have to completely compensate it. Then you will be able to see a circular rotor. Okay. Otherwise, with this condition, it will be a elliptical rotor. Okay. And then it is capable of causing 1x and 2x vibrational components. So unless you properly compensate these slots, you will end up seeing 2x vibration, which is not good. So I have seen some manufacturers, they didn't compensate these slots properly. So we ended up getting 2x vibration. Then you cannot operate the machine. That's the bottom line. So you need to recognize these dissimilar stiffness effects in a generator rotor and properly compensate. Okay. And then this is the final analysis, mode shapes, and how you calculate responses, how you do rotor stability analysis, etc., etc. In a steam turbine, we do the model analysis: first rotor mode, bending mode, and second mode, conical mode. Okay, those are the rotor frequencies, like I discussed before. And the unbalanced response is basically if any rotor, they cannot be completely balanced, so you have some kind of imbalances caused during assembly. For example, we are assembling blades on a rotor, that can cause an imbalance in the system. Or you are not properly aligning the rotor systems, that can cause eccentricity, and that will trigger the imbalance, mu omega square, basically. Okay, so that can cause vibration. So if you plot the unbalanced response, this is the rotor speed, this is the amplitude, and up above you see the rotor speed and the phase angle. Okay, so you plot all the rotor speeds, and you see that at one point the rotor reaches high amplitude. Okay, that's the frequency, that's the natural frequency. That means the rotor is reaching a resonance there, and then once it passes that, it comes down. Amplitude is almost to zero. Okay, is in life also, you will see that people end up seeing peaks and valleys in their life. So it's not going to stay. Your life is going to move on. When you think that way, the worries are going to disappear. Okay, just a life's example. um, the rotor stability is basically, in a rotor supported in oil film bearings, it can cause rotor whirls. Then that rotor whirl can become rotor whip. So that's not good, because it's causing high vibration. This is the characteristics of the oil film that is causing the rotor stability. So you should be cognizant of the effects, and then you have to calculate rotor whirl modes and find out which frequency is affected. Usually it affects the subsynchronous frequencies. The subsynchronous frequencies will just shoot up if there is a oil web. Okay, so you have to recognize that condition. So you have to use proper methods to reduce vibration. So basically, what we have discussed here is that if a rotor designer must investigate three important parameters for successful operation. So unbalanced response, critical speeds, rotor stability or instability. That's also important, because when you support a rotor and oil film bearings, especially partial arc bearings, they are all susceptible for oil web. So you need to recognize that. Okay. So with that, I complete this session, and I'm planning to talk another session also, if you are willing. Um, so this is the book I published, Springer published. There's a lot of information in there. If you are interested, you can purchase this book and read. And yeah, at this point, I would like to open the podium for questions.
Okay, thank you, sir. Very good session. Some questions is there. I will show in your screen.
Mr. Murugan asked to sir how to
Sir, sir,
fix the node how to fix the
sir,
node
sir,
point on rotor type
please wait.
component at which method?
Yeah, your words are breaking. Can you please talk slowly? I can listen.
Yes, sir. Yes, sir. Mr. Murugan asked to you how to fix the node point on rotor type component at which method used.
Sir,
The
this is
Oh,
question is
this
in your screen.
in your screen, sir. If you able to see the question in your screen, sir. Please minimize your PPT.
oh, okay.
Go to the screen as screen. You able to see the question.
Okay, just 1 second, 1 second. I'll do
Okay.
that. Hmm, Why? I don't see. Oh, okay, okay. Here you go.
Yes. Okay.
Yeah, yeah. Okay. Yeah, yeah. Show me. Yeah. Okay.
Okay.
So, how to fix the node point on rotor type component at which method? Okay, you are basically asking how to fix the node point on a rotor component and what method is used. Actually, you can perform model analysis, okay, mode frequency analysis, and plot the rotor modes. Okay, that way you will see the. I can show you from my presentation. Uh, okay, let me do that. So that way it's easy. Can you see my screen? Can you see my screen?
Yes, sir.
Yes,
Yes, sir.
sir.
Okay. Yeah. Okay. So for here, you see that node points. You see a node point here in the middle. Node. So you have to plot this mode check in order to find out what node points are. See, for example, in a lateral analysis, you will see one node here, and then another node, another node. Okay. So in order to get this, you have to perform model analysis and plot the mode shapes. Is it clear?
Okay, sir. Next question is there.
Okay.
Uh, wait,
Yeah, go
Mr.
ahead. Yeah.
Okay.
Can we use Fluent, Gambit, and Abacus software to do? Yeah, you can. Yeah, you can very well use the Fluent mostly for fluid dynamic analysis. But no, I heard about Gambit and Abacus. I'm very familiar. So you can use either one. You can use any of those to calculate your vibration analysis. Yes, you can do
Okay,
that.
sir. Next question is
ODS. Um, ODS. Operating displacement. Is that the thing you are talking about? Operating displacement check. Is that you are asking?
yes, sir. Yes, sir.
Yeah. So basically, ODS you can do that while the machine is running. You can measure vibration at different points and then plot it. So that provides you the ODS class. We can use ODS class. Okay.
Okay, sir. Next question is that
On which workbench software used for this analysis? On which workbench software used? Which analysis are you talking about? For the vibration analysis, is that the question?
Yes, sir.
Of course, you can use workbench software. So that, I mean, you are asking whether you can use workbench software for vibration analysis. You can use it.
okay, sir. Thank you. Now the question is over. Pawan sir, please.
Sir, first of all, I very deeply regret to all. I very deeply regret to all participants for inconvenience, and I would like to thanks our speaker for such a informative session. They give a very nice presentation in front of to us, and very nice information, and very nice information. I would like to thank our speaker for such a informative session, for our HOD sir, Mandsaur University and management, and finally all participants who participated actively and patience. Thanks to one and all, and I especially thanks to Mr. Praveen Bhargav sir, who uh, take the who very who take the responsibility for these issues and overcome the all issue, and very thank to Praveen Bhargav sir. And once again I thank to speaker sir and all participate and Mandsaur University. Thank you so much.
I really, really appreciate, and I would like to get your feedbacks on it. And I was thinking of presenting other part also due to time constraints. We can do it later or some other time about the diagnostic tools, but not this time. This is fine. Yeah, thank you so much for patiently listening to me because there are a lot of problems, hurdles, and hope I also learned how to sort out these problems. Thank you so much for all of you.
Okay, sir. Thank
Thank
you,
you
sir.
sir.
Thank you
Thank
very
you.
much.
Thank you.
Okay.
We are
Bye.
ending the session, sir.